organizers of Global NMR Discussion Meetings for this wonderful opportunity to present our recent work on long-lived spin order in aliphatic chains. So on this slide, you can see a brief outline of my talk. I will talk mostly about quantum delocalization of long-lived spin states in aliphatic chains. And I will go through theory, curiosity, and difficulty of understanding such experiments, if I may say. And then we will proceed to methodology and applications of such experiments. So first of all, you can imagine a molecule which contains a short aliphatic moiety placed in high magnetic field. And because of the high magnetic field and because of the substitutes R1 and R2 are different in this molecule, the chemical shifts of these protons will be very well separated so that we can address these aliphatic groups separately. So in experiments which I will introduce, we will apply some selective pulses to address these CH2s separately or altogether. And in a way, I suggest to think about such experiments as an analogy that we can place a phone call. So we can call to individual CH2 groups and say them something. And wouldn't be this wonderful? For example, think about experiment like this, where we first call to the CH2 group next to R1. So imagine such a conversation. Hello, can you hear me? Is this a CH2 group next to R1 substitute? Yes, great. Then we have some news for you. Please change your state from magnetization to some spherically isotropic state, because we have some very strong filters consisting of hard pulses and gradients that will destroy any magnetization pointing along any direction. And if you don't do this, then your NMR pressure signal will be destroyed. And while we were talking, the spins actually change their state to be isotropically symmetric. And then we will place another call and ask them, please review your state. And then we observe a nice NMR signal coming from this CH2 group. Now, imagine that instead of calling to the same CH2 group, we will actually place a phone call to another CH2 group, which is not directly connected to the initial one. So it should not know anything about our conversation. And in principle, we expect to see nothing for this CH2 group. But when we ask them, do you have any isotropically symmetric state? It turns out that they actually do have it. And I find this fascinating, and at the same time, it's very difficult to understand why is it happening. So in my talk, I will try to provide some theoretical explanations which might be of interest for you. There is another interesting experiment where you can call to all CH2 groups at the same time. And when you do this, actually the spectral appearances changes a lot. So instead of a single singlet signal, there will be some multiplets. And these multiplets are very consistent with theoretical calculations which are shown in blue. So in black it's experiment and in blue it's simulation. Okay, so how do we understand all these experiments? In order to proceed, I will first would like to introduce the concept behind parahydrogens, so-called spin isomers of dihydrogen molecule. So as you might know, parahydrogen is a spin isomer of dihydrogen molecule, which constitutes the singlet state of individual spins. And orthohydrogen This is a molecule where the protons are in triplet, one of the triplet states of the molecule. And by cooling down this dihydrogen molecule to cryogenic temperatures in presence of a catalyst, it is possible to overpopulate the parahydrogen state, and then by warming it up to room temperatures and above, we can observe one interesting thing. This is the situation where parahydrogen is conserved for many days and relaxes very slowly to orthohydrogen state. Why is this happening? It turns out that the dominant relaxation source for such situations is intra-pair dipole-dipole coupling between the two hydrogen spins. And it's symmetric with respect to intra-pair spin permutation. And therefore, it cannot cause this type of relaxation. Now, there is yet another very interesting property which concerns the wave function of parahydrogen or orthohydrogen. So imagine you have a composite particle which consists of two particles, A and B, and then the composite particle, the state of this composite particle, will be described as a linear combination of states spanned by states of individual particles. And in case of parahydrogen, this would be for individual protons, you have alpha and beta. And for the parahydrogen, there will be 4 states, alpha alpha, alpha beta, beta alpha, and beta beta. Now the question arises, are there such states of the individual particles such that their linear combination, the product of the coefficients CAI times CJB will be equal to the coefficient Cij for all the coefficients? And if this is the case, then the state is called to be separable. So one example of a separable state is alpha-alpha state or triplet plus state. So in this case, the vector representation of this state is 1, 0, 0, 0. So alpha-alpha is 1 and zeros for the rest. And this state can be composed of the initial of the constituting particles being in alpha state. So spin A in alpha and spin B in alpha as well. So the product, the tensor product of these two vectors will produce exactly this vector. However, we cannot say the same thing for the singlet state. Why is that? It turns out that in a very general form, when you take the direct product of any state of particle B and particle A, they will produce a column vector like this, C alpha A, C alpha B, C B A, C alpha B, C alpha A, C B beta, and C A beta, C beta B. But as you can see from the first row, this coefficient must be 0. Okay, so that means that either spin A in alpha, coefficient C alpha A must be 0, or coefficient C alpha B must be 0. But it cannot be, because the second line here tells that C alpha B is not 0, and the line 3 says that C alpha A is not 0. So we end up in a very strange state which cannot be reproduced as individual states of individual particles. Now, this is called inseparable state or delocalized state, or another name is entangled state. And it turns out that in such delocalized states, the particles somehow lose their identity. So whatever you do with one particle will change the state of another particle. And it turns out that something similar may happen to protons in aliphatic chains, as you will see later on. So what about NMR? A typical spin pair in NMR will be a weakly coupled spins A and X, and their eigenstates are described as Zeeman product states, alpha alpha, alpha beta, beta beta, and beta alpha. However, there are some cases where the two particles are strongly coupled, very strongly coupled. And in this case, the state will be described by three states which are very close to three triplet states, which are symmetric with respect to intrapair spin permutation, and one singlet state, which is antisymmetric with respect to intrapair spin permutation. Now, the memory of spin system is governed by longitudinal relaxation, which equilibrates the population within the triplet manifold. And it turns out that if you can create imbalance between triplet states and singlet states, this state will be long-lived, which was discovered in the group of Malcolm Levitt back in 2004. Now, how we can understand this phenomenon? We must consider the symmetry of spin Hamiltonian. And in general case, the Hamiltonian will consist of a coherent part and fluctuating part. The coherent part consists of Zeeman interactions with the radio frequency pulses, Hamiltonian terms which describe J couplings, and so on. It's very important that some of these interactions must break the symmetry of the spin system. So we call these ungerade terms, which in German means antisymmetric. And using these ungerade terms, then we can create imbalances between states belonging to different symmetry. Then we need to suppress these terms, and we leave the system to evolve under Gerade terms, so under symmetric part of the coherent terms of the Hamiltonian. Now, what about fluctuating terms? Fluctuating terms, they are time dependent, and they are different for every member of the spin ensemble, so for molecules in an NMR tube, and they usually consist of dipole-dipole interactions, Hamiltonian describing dipole-dipole interactions, chemical shift anisotropy, and some others. So it's very important that the relaxation mechanisms which cause the dominant contribution to relaxation must be symmetric with respect to spin permutations. And if all these conditions are fulfilled, well, congratulations, then probably there will be some accessible long-lived states observed in NMR. And in this talk, I would like to concentrate on a specific type of system where all these conditions are fulfilled, which are aliphatic moieties. So first of all, the fluctuating term of the Hamiltonian, which is dominant mechanism for the spin relaxation, is intrapair dipole-dipole interaction between the closest protons, so locating on one CH2 group. So this dipole-dipole relaxation mechanism will be inactive during long-lived state experiments. Then we have the dominant interaction, coherent dominant interaction, which is also geminal interaction between the spins located on the same CH2 group. And in addition to this, we need, as you remember, some symmetry breaking terms. And these symmetry breaking interactions come from vicinal interactions between the neighboring CH2 groups. So as you can see here, the J coupling between spin A and M prime and A and M are different because they depend on this torsion angle. And in solution, of course, there is a very quick rotation around CC bond, which leads to different configurations and different values of those couplings across the rotamers. it turns out that if the energy of this anti-configuration is different from the energy of these gauche conformations, then the difference of these J couplings will be non-zero, and the spin system of the aliphatic chain will be AA prime, MM prime, XX prime according to Popov's notation. This property was discovered by Schrumpf back in 1972. We proceed with experiments on molecules containing short aliphatic chains, and we discovered that there are many molecules out there which actually have accessible long-lived states. And many of these molecules are bioactive, such as GABA, beta-alanine, acetylcholine, taurine, homotaurin, and so on. We also discovered that some molecules didn't have accessible long-lived states, probably because their rotamer energies were equal. Now let's proceed with the theory of a simplified aliphatic chain. We will consider the spin Hamiltonian of aliphatic chains, and we will assume several important items. First of all, we assume that each CH2 group is weakly coupled to its neighbors. And we also assume that each pair is magnetically inequivalent, forming systems like AA prime, MM prime, XX prime. Additionally, we assume a translational symmetry across the chain, so that all geminal couplings are equal between the protons, and all delta J's are equal for each pair of CH2 groups. Under these assumptions, we can split our Hamiltonian into three terms. The first term describes geminal interactions within the pair, and this is the dominant term, as the J geminal is much larger than delta J's normally. The last two terms describe vicinal couplings, and we split them according to the symmetry. So the first term is symmetric with respect to intrapair spin permutation, and the last term is antisymmetric. Each CH2 group, when it's isolated, is described by 4 energy levels, 3 triplets and 1 singlet state. Now, it turns out that for the assumptions which we made, the mixing of the outer triplet states doesn't matter. So we left with just 2-level systems like this, which greatly simplifies our treatment. And we can think about all these 2-level systems as fictitious spin 1/2 particles, which are separated in energy by geminal J coupling. So singlet will be fictitious state alpha, and triplet will be fictitious state beta. Now, the first two terms of the Hamiltonian commute, and they have eigenstates which are simple products of those states. So things like singlet, triplet, singlet, 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 and so on. The last term of the Hamiltonian, however, doesn't commute with the first two, and it introduces certain type of mixing between some of the states. Namely, there are 2 types of mixing. The first mixing occurs whenever a wave function contains a triplet next to singlet, and it will be mixed with the state is the identical state where these 2 states are swapped, so singlet, triplet. The second type of mixing occurs whenever the basis state contains triplet next to triplet. It will be mixed with a similar state, but where the states are swapped with the singlets. As an example, you can see here the Hamiltonian of 4 CH2 groups, and we order our basis functions in such a way that there will be blocks containing only 1 triplet state, which located at position 1, 2, 3, and 4, or only one singlet state, also located at shifting position. And the first type of mixing occurs between degenerate states. And the second type of mixing occurs between manifolds of well-separated states, as the 2J geminal is always much larger than delta J divided by 2. Now, this situation is very similar to a case of so-called XY model, where we consider a chain of spins with the nearest neighbor interaction, spin 1/2, coupled through a non-secular part of the J Hamiltonian. The matrix representation of such Hamiltonian has very similar appearance to the Hamiltonian of our aliphatic chains, namely the non-zero elements exactly above and below the diagonal. And these are very good news for us because XY model was studied extensively over 20th century, and there are many things are known about this system. In particular, we can actually diagonalize such matrices analytically. And this slide shows you the analytical expression for the eigenstates of such matrices. So we have a superposition of our basis functions weighted by a sine function with a distinct wave number. And we can plot coefficients of these functions, how they distributed along the chain. Here you can see an example for 10 CH2 groups, first 4 wave functions. Now, if we come back to the case of 3 CH2 groups, here you can see the exact expressions for the 3 delocalized states that are found in these systems. Normally, these states are not populated and do not affect spin dynamics. However, under the action of these selective pulses, which are chosen to have very specific amplitude and duration, it turns out that these states are actually populated. So whenever we radiate spin pair A prime, these 3 states are gradually populated. And if we stop our selective pulse at this moment, we will have a significant population of these delocalized states. And if we start with this state and start to place the selective pulse on the remote CH2 group, then we will convert this delocalized state into observable magnetization. Actually, it turns out that these delocalized states somewhat similar to the singlet state of parahydrogen. They also cannot be represented as a direct product of pure states of constituting particles, meaning that they are inseparable. So that means that whenever you're talking to one CH2 group, you're actually talking to all of them, and they all listen to you very carefully. Well, this phenomenon provides somehow the explanation for the observation of this delocalization experiment. Now, it turns out that there is a complementary explanation, which I will now introduce. So let's first consider spin dynamics under this polychromatic spin lock-induced crossing, or triple slick. These selective pulses must have very specified amplitude, namely either 1 J geminal or 2 J geminals, and very specific duration. Why does this happen? In order to understand this, it's very useful to consider so-called level anti-crossing diagrams. So imagine that we irradiate 3 CH2 groups at the same time, and the Hamiltonian of such irradiation in a triplet rotating frame is as follows. And we plot the eigenenergies of the Hamiltonian as a function of the notation frequency. Then there will be families of lines corresponding to so-called dress states. There will be a family of dress states with the total spin 3, and there will be a family of states, dress states with a total spin 1. And when we set the RF amplitude equal to J geminal, it turns out that there will be level anti-crossing occurring between these two families of states. And it turns out that for triple slick irradiation, the level anti-crossing occurs between states that are different in their projection number by number 2. So we call this double quantum level anti-crossings. However, if you irradiate only one spin pair, then there will be a similar level anti-crossings appearing between states, between dress states that are different by their projection number by unity. So we call this single quantum level anti-crossings. And as you can see, this level anti-crossing occurs at very specific frequencies in terms of radio frequency amplitude. So either J geminal or 2 J geminals. Now, whenever you switch the Hamiltonian abruptly from 0 to this level anti-crossing region, there will be coherences induced, initiating transitions between states of different symmetry, so that you can populate imbalances of states belonging to different symmetries. And we can see this in simulations of density matrix excited, for example, by triple slick. So the local symmetry of each CH2 group can be ungerade or gerade. So triplets are symmetric, singlet is antisymmetric, as you remember. Now we can order the basis functions according to their symmetry, and we see here that we overpopulate states which contain 2 singlet states, but we depopulate the manifold which contains 3 triplet states, and we overpopulate the unique singlet, singlet, singlet state, and we depopulate states that contain only 1 singlet state in them. So here you can see that actually we're depleting a common reservoir for all CH2 groups, and therefore, whenever you will reconvert such a state, each CH2 group will see, oh, I see that there is less triplets than singlet, triplet, singlets, let's say. And this also will lead to delocalization of our signal, long-lived state-derived signal. Okay, so now let's proceed with understanding of the experiments. In this slide, you can see experiments where we prepared long-lived states on different CH2 groups, and then we read out these long-lived states always on the same CH2 group. All the experiments, first of all, show that the fraction of the signal is pretty low. It's up to 6% of the thermal polarization, but all of these signals decay very slowly, on the order of 9 to 8 seconds, which is much larger than relaxation time, T1 relaxation time for the studied system. Now let's talk a little bit about some applications. One of the remarkable applications of such long-lived states is a ability to reveal contrast upon binding to biomolecules. So imagine that you have a molecule where you can excite these long-lived states, and this molecule binds to a dilute protein. And when it binds to a protein, the local environment of this CH2 group is changing abruptly, so that the singlet and triplet states are no longer the eigenstates, so they dephase very quickly. And we observe this free form of the molecule, and the observed relaxation rate of this will be a population average between free and bound form. But because the relaxation rate of the free form is extremely small, and the relaxation rate in the bound form is extremely large, we can actually observe some contrast even in large excess of free ligand. Here you can see experimental results on such experiments. So we performed titration series between molecule called DSS, so it's aqueous standard in aqueous solutions. And this molecule binds to a protein called bovine serum albumin. When we measured the lifetimes of the long-lived states as a function of protein concentration, we saw that the lifetimes decreased dramatically. And in particular, for this point, we have a ratio of molecules of DSS to BSA molecules to be 10,000, but we see about 40% of the contrast for the long-lived state. For the standard experiments, which are normally used to reveal such kind of binding events, namely R2 experiments, the contrast is lower. Now we can also make experiments where these long-lived states excited in parallel in several molecules, where we have a mixture of molecules with aliphatic chains. Sorry. And we irradiate several of these molecules and create long-lived states in them with a sleek pulse, which has averaged duration between optimal durations for each of these molecules. Now, here you can see a spectrum of long-lived state derived signals, and for 4 of these molecules, we could observe nice signals, but for one of the molecule, the sleek duration was not very optimal, so for beta-alanine, it didn't work very well. But for the 4 other molecules, we were able actually to observe the decay of long-lived states in parallel. Now, I would like to also discuss quickly a source of MRI contrast using long-lived states. In these experiments, we had a concentric NMR tubes, one NMR tube containing homotaurin, solution of homotaurin, and one NMR tube containing GABA. In these experiments, it turns out that GABA and homotaurin, they reveal CH2 group on the same rate, right? So the spectrum of these 2 molecules contains overlapping signal coming from GABA and homotaurin, and this signal we will observe. However, on the excitation step, we will irradiate only signals of GABA or only signals of homotaurin. And by doing this, we encode the singlet states or long-lived states in either homotaurin or GABA. And then you can see that indeed the cross-section of this MRI image contains signals coming only from GABA, which is located in the outer NMR tube, or only from signals coming from homotaurin, which is located in the middle. Okay, with that, I would like to conclude, and I would like to thank my colleagues, Jeffrey Bodenhausen, Anna Zonnefield, Filippo Pelupesi, Ike Rosenhaer, and others. And thank you for your attention. Thank you for your patience. And I just want to say that we are looking for PhD students and postdocs. Thank you so much.
Thank you very much, Kirill. So we already have one question from Malcolm. So he's asking, under which condition, if any, could one expect soliton-like propagation of spin order along the CH2 chains?
Yes, this is actually excellent question. It turns out that whenever you create a different non-uniform distribution of singlet states along the chain, there will be propagation of spin order back and forth between CH2 groups. And it was initially shown by Stefan de Vins in 2016, and then we discovered that similar phenomena can occur in longer aliphatic chains. For example, I have a slide here showing this type of propagation of singlet states across the chain, where you, for example, excite singlet states on only two adjacent CH2 groups, but then you decouple the third one, so you don't create anything here. And then this non-uniform distribution of singlet states will start to propagate. I hope this answers your question, Malcolm.
Thank you, Kirill. I answer for Malcolm. I have a question on my side. So it's not related to that question, just for the last slide for the imaging. I was wondering, so you're using gradients to select some slices, I guess, in your tube. So what machine do you need for that? Do you need a high field spectrometer? Is it doable with benchtop NMR spectrometers, or do you need strong gradients?
Right. This is high field NMR spectrometer. We did it on 800 megahertz, and it's much more difficult to do on benchtop NMR machines because the CH2 groups will come much closer to each other. So the chemical shift separation will be very small. You need separation of CH2 groups in this type of experiments. Yes.
I see.
Thank you for the question.
Thank you. And I have another question. Thank you for your answer. On the drug screening, so you mixed a lot of ligands in the sample, and my question was, what is the limit of that approach? How much molecules can you selectively still excite with SLIC and still visualize their interaction separately without overlapping? What is the limit in terms of numbers of molecules you can mix?
Very, very good question. Thank you, Charlotte. So the limit is that you apply selective pulses with a notation frequency of approximately 30 hertz. Then the separation between the groups must be much larger than this, so that if you can find the CH2s which are located far enough, so let's say 100 hertz apart, then you can proceed. Then there is another constraint which comes from the fact that you irradiate with the same duration pulse. And these conditions for conversions should be similar. So for example, here we had 4 molecules for which duration of SLIC pulse was comparable, but the duration of the SLIC pulse required for beta-alanine was actually much longer. Then you will lose a lot of intensity. Yeah.
Okay, thank you. So in the chat, Malcolm has another question. So in reference to the enhanced damping of long-lived state when a ligand is bound to a protein, has the mechanism been identified?
Oh, this is a very good question. Just 1 second, I will. So there are some works by Nicola Salvi and the group trying to identify this type of source of contrast. And in their system, they applied strong spin locking pulse to suppress inequivalence of the spins in free form. And then they were speculating that in the bound form, the chemical shift of those protons will be shifted a lot and will not be effectively sustained. But it turns out that in our experiments, we don't use any spin lock to sustain the singlet states. And honestly, we don't know what is the source of the contrast. Probably the symmetry of the system somehow changes in the bound form. So there will be a lot of local fields which induce local fields at the area of these two protons, making them inequivalent. So this can be some fluctuating terms like dipole-dipole interactions, but also probably J couplings and chemical shifts of these two protons may also alter. But it's very difficult to simulate this type of fluctuating terms.
Thank you, Kirill. On this slide, I had another question. So you showed that the signal is 6% on average, I would think, of the thermal equilibrium.
Exactly.
So for the drug screening, what is the minimal concentration you could use to see LLS contrast? And I guess you would access weak affinity binding. And if you want to access a stronger interaction, I don't know if it's in your plan, do you think on using hyperpolarization with LLS?
Yes. So indeed, this is a problem of such experiments when you think about practical applications. And it turns out that when we used spectrometers with the cryoprobe, we could go down to approximately 250 micromolar solutions and still detect long-lived states of such molecules. Then we actually did some experiments on hyperpolarization. So for example, dissolution DNP produces these hyperpolarized long-lived states. And this helps a lot in terms of going down in concentration. And recently, we also did some experiments on photokidney of these long-lived states. And in collaboration with the group of Roland Rick, where they could detect this type of long-lived state signals coming from molecules at about 50 micromolar concentration of the ligand, which is actually very low concentration, and it's absolutely relevant concentration in terms of drug screening experiments.